So here in this, consider a chemical reaction is being carrying out in a tubular reactor, tubular fixed bed reactor with the inner radius R as shown in figure. So reactor, the boundaries of the reactor is varying from -infinity to +infinity. It is divided into 3 zones. So this is the reactor. So this is tubular reactor of radius R. This is the radius R. So this is the diameter and this is the wall of the reactor, and it is divided into 3 regions. Okay, this is zone 1, zone 2 and zone 3, and this is -infinity is here and +infinity is here. Here Z equals to 0, here Z equals to L. So entrance zone packed with a non-catalytic sphere. So what is the purpose of entrance zone is so that there should be a uniform flow distribution as well as temperature, energy distribution. Uniformly it should be there actually, that it is packed with a non-catalytic inert particles. Just uniform distribution of all the properties, that is the main importance of this entrance zone. And zone 2 is a reaction zone. So this is zone 1. It is packed with a non-catalytic inert particle. So the importance of this zone is, so all the properties like velocity, temperature, it will be even radially. Radially, there will not be any variation in temperature and velocity when it is reaching this catalytic particle. And this is zone where catalyst is filled. So what is happening in catalyst? So this catalyst, the zone extending from 0 to L, and exit zone, again same thing. So there might be uneven reaction and everything in this zone, packed zone. So to distribute all the properties evenly, so again that non-catalytic sphere is kept at the end. So and here you will get a uniform distribution of all the properties in a product. So it is assumed that the fluid proceed through the reactor tube in a plug flow. So this is again assumption. So plug flow, we are assuming perfectly plug flow, and axial velocity is uniform at a superficial value. So axial velocity, superficial value means kind of average velocity, superficial average velocity. Average velocity will be equals to mass flow rate divided by cross-sectional area divided by density. So this will give you a superficial velocity. The density rho, mass flow rate W, and superficial velocity V0. The heat capacity per unit mass at constant pressure. This all the time you should represent this cap, at least whatever topics we are considering, if cap is there, it will be per unit mass. So this is heat capacity per unit mass are treated independent of R and Z. So we are not considering that variation of specific heat, okay, heat capacity with respect to R and Z. In addition, the reaction is assumed to be, a reactor is assumed to be wall insulated. So this reactor is wall insulated. So here this wall is insulated. So here I have catalytic particle, and so on. So when the chemical reaction occurs, the thermal energy is produced or consumed when reactant molecule rearrange to form a product. Consider a volume rate of heat production by chemical reaction as a function of temperature. So this function of temperature, heat generation is a function of temperature SC as given by this equation 1. So this heat generation is a function of temperature, and f of t, here it is given f of t can be anything. It depends upon a given reaction. So function of temperature. So here f of t equals to t minus t0 divided by t1 minus t0. This function of temperature, some arbitrary, it can be any arbitrary function. Can be any arbitrary function also. SC is it depends upon a temperature, function of temperature. So when chemical this is given by where SC1 and T0 is the empirical constant. These are some constant, empirical constant T0, and T1 is the input temperature. T1 is input temperature. find steady state axial temperature distribution. Find steady state axial temperature distribution Tz when fluid enters at Z equals to infinity at a uniform temperature T1. This is the input temperature. Discuss with figure how temperature profile will change for a different value of empirical constant n, which is given in equation 2 below. So, how this different value of n will change the nature of temperature profile, that we need to discuss. Also verify how temperature profile can be obtained for an arbitrary f of t. This f of t can be anything. In this problem, it is given t minus t0 divided by t1 minus t0, but it can be any arbitrary value. So how we can get a temperature profile if f of t is any arbitrary function in volume rate of heat generation, rate of energy produced term. Actually, this f of t is any arbitrary function. This is given problem. So what you can take the information from this. Roll number 1, Abhinav. Abhinav, roll number 1. Are you able to hear me? Roll number 1. Roll number 2, Abhishek.
Hello, am I audible, sir?
Yeah, you are audible. Can you just tell whatever you can, take out the information and just give the idea how to solve this problem?
A chemical reaction is occurring in a plug flow reactor, and we have it is of infinite length, and but the reactor is only in like the reaction is only occurring in Z is 0 to Z equals to L, and we will apply the shell energy balance in the region.
Shell energy balance equation. First of all, you need to apply shell energy balance equation, and
Yes,
here
sir.
variation of temperature is there only in Z direction. Okay, this is the
Yes.
figure. There is a variation of temperature in the Z direction, and there is a flow of reactant and product also. So here we are getting reactant, and after here we are getting reactant and product. Flow is there. So what will be considered? Whether convection will be considered, conduction will be considered, or what need to be considered?
Uh, so the total energy flux, like
Total combined energy flux. So
yes, sir.
whenever there is a flow, so this is thumb rule. Whenever there is a flow, we'll start the problem with combined energy flux, and then we'll add all the assumptions. Okay? Whenever there is a flow, because here there is a flow and we are discussing temperature variation in a direction of flow. So we'll start with a combined energy flux. This is first thumb rule. And second thumb rule is there, whenever there is a reaction, because there is a reaction also. So we are discussing temperature variation in Z direction, but there is reaction also. We are not interested in mass transfer as of now. We are interested only in heat transfer. So reaction is there. So what will happen? This internal energy of reactant, internal energy of product, specific heat of reactant, specific heat of product, these are different. Okay. So whenever there is a reaction, instead of internal energy, it is better to use enthalpy. Enthalpy can be a better scale to justify the energy content of the mixture of reactant and product. Enthalpy. Okay, enthalpy can be a better scale to justify energy content of mixture of reactant and product. If you have pure reactant or pure fluid, then we can handle the energy content by internal energy. So this you might have been studied in thermodynamics. Okay, thermodynamics. Whenever there is a mixture, so internal energy only or total energy content can be better handled by a enthalpy rather than internal energy. Okay, enthalpy can be a better scale. So we are not going deep into that detail, that information, how that mixture enthalpy will be better than internal energy. And if you have pure compound, internal energy is better than enthalpy to justify energy content of the molecule or energy content, volume energy content of a given compound. Okay, so we'll handle this problem better with the enthalpy rather than internal energy. So these are the two thumb rule you need to use in heat transfer. Whenever there is a flow of material is there, so you will be using combined energy flux. And as soon as there is a reaction in a given product, but we are interested in heat transfer. So reaction is there, but we are not interested in mass transfer here. We'll discuss mass transfer problem also. Here we are interested in heat transfer. So as soon as there is a reaction, because this composition of this stream is changing, the composition of stream is changing from input to output. Composition of stream is changing. In such a case, instead of internal energy, so it's better to handle the problem using enthalpy. Enthalpy. So this is what shell energy balance equation, because this is flow system. So we will handle this problem using combined energy flux, because there can be a conduction also, convection also, and work associated with that, and this will be all external forces which is adding work and done, and this will be rate of energy production. So this is overall shell energy balance for steady state. So whenever there is a flow, we'll combine all these three and we'll use a combined energy flux. So we'll be using a combined energy flux. This is first thumb rule, and this thumb rule will be used for flow system. If the composition of the mixture, composition of compound is changing, okay, this material, here I have reactant, say here I have, say oxygen, and this slowly it is converted to carbon dioxide. So here we will have oxygen and carbon dioxide. Slowly there will be change in a composition of mixture. In such a case, instead of internal energy, where internal energy will come, internal energy will come in a convective transport, actually convective transport. So yesterday only we have discussed, it consists of internal energy per unit volume rho into u and half into half v square, that is actually kinetic energy per unit volume and internal energy per unit volume. Instead of that internal energy per unit volume, we will be using enthalpy. Okay, combined energy flux. So this is the combined energy flux, half rho into v square. So rho into v u. So this will be a total energy content, and this we will be using whenever there is a flow system. Whenever there is a flow system, we will be using this actually. So but as now we have a reacting system, so instead of internal energy, we will be using enthalpy. We will be using enthalpy, and this equation and this equation is same. And this internal energy is not equals to enthalpy, but this is rearranged. You can see this is total molecular flux. This is total molecular flux, where this is the molecular flux because of viscous forces. Okay, this is total molecular flux, which consists of molecular flux because of pressure forces and molecular flux because of viscous forces. So this is written in two components, and one component is added with this internal energy to get this enthalpy. This pressure component in this total molecular flux. Okay, this total molecular flux consists of two components. One component is a molecular flux because of pressure forces, and another component will be a molecular flux because of viscous forces. This is tau is a molecular flux because of viscous forces, and this molecular flux because of pressure forces will be added to this. Okay, so can you try this? How to get this equation from this equation? Very easy actually. So I have this total molecular flux, which consists of a molecular flux because of pressure forces and molecular flux because of viscous forces. Now substituting it here, okay, pi dot v will be equals to pv, okay, this will be a p dot v, again tau dot v. This will be equals to this. Now substituting this two component here, substituting this two component here, and I have rho u v plus pv. That can be written like rho constant, and this will be a p divided by rho. P divided by rho. This will be, you can say, a volume per unit mass or specific volume. Okay, this is a volume per density can be written like a volume per unit mass. Volume per unit mass. Okay, you can write like this: 1 upon rho equals to v bar. Okay, volume per unit mass. So u plus pv is h. H equals to u plus pv. So this u plus pv is h, and I can write same equation with this, actually enthalpy. I'm going to use this equation. So whenever I have flow system, simple flow system with no change in the composition of my material, then I will be using this combined energy flux. But if I have change in the composition and more energy interaction is there with the pressure also, pressure and energy content is related, then I will be using enthalpy. Not only this composition change. So you need to decide pressure, how pressure is affecting on energy content and all. If that is playing some role, so instead of internal energy, I will be using enthalpy. Enthalpy. So this will be kind of a convective flux, and some effect of a molecular flux is also there actually. And this is molecular flux, and not molecular flux. This is a work associated with a molecular transport, and this is the conductive flux actually, conductive flux. So this will be the equation we will be using whenever there is a change in composition or pressure has some role to play, major role to play in overall energy content of the system. Okay, so we will be using this. This is clear to everybody? Roll number 4, Aditya.
Yes, sir.
Yeah, when to use this equation, first of all?
Sir, this when there is we are dealing with convective system.
We are
Hello?
dealing with the
With flow. Whenever
with
there is
flow.
flow in our system, we will be using that first equation. And if there is any reaction happening in our system, then we will convert the internal energy into enthalpy.
Yeah, enthalpy. And this is actually this enthalpy, this pressure fluxes. Pressure
Yes.
fluxes is added to internal energy. So you can see this total fluxes and all. This is just a rearrangement. H equals to U plus PV again. This is clear now? Okay. So we'll start with this equation. Okay. So now again, moreover, how to get this rho into H? Okay, how to get this rho into H? So you need to go back to all your thermodynamic relation. So rho or H, how to get this H? Enthalpy by using a specific heat and all. So this is one of the thermodynamic relations. So there are so many thermodynamic relations. dH will be equals to dH by dt constant pressure dt plus dH by dP at constant temperature dP. So this is the one of the relation using which you can get the enthalpy or variation in enthalpy. Now dH by dt at constant pressure can be represented as a specific heat. Okay, heat capacity or specific heat capacity at constant pressure, heat capacity at constant pressure per unit mass. This is heat capacity at constant pressure per unit mass, and dH by dP at constant temperature will be equals to specific volume. This volume per unit mass minus T dV by dt at P. So these relations you might have gone through, or these are from thermodynamics. Okay, thermodynamics relations are there. So from there you will get actually. Now to get H or rho H, I will be integrating this equation, integrating with reference to some reference condition. Okay, with reference to some reference condition. Say at reference condition at temperature T0 and P0. These are the reference temperature, pressure, temperature and pressure. Reference condition, temperature and pressure is T0 and P0. Enthalpy is H0. If this is given, then I can get this enthalpy. If this is given, then only I can get. So these are the reference condition enthalpy. These are the reference temperature T0, reference pressure P0. If I integrate this equation, so what I will get? So H minus H0 will be equals to H minus H0 equals to Cp T minus T0 plus P minus P0, and this is specific volume. As this is constant with respect to pressure, you can see. This is constant with respect to pressure. So this will be eliminated from the equation. Only P minus P0 into V bar. Again, these are the constant with respect to pressure. Okay. This V bar is constant with respect to pressure. So whole is constant with respect to pressure. So you will get this equation. All this I think this will have zero value. Integration from this. So this is P minus P0 into V bar. Now rearranging this equation, what I will get? Multiplied by rho. So this is H. Okay, this is enthalpy at a given condition minus enthalpy at a standard condition will be equals to Cp T minus T0 plus P minus P0 V bar. Okay, so multiplying it by rho, so it will be a rho Cp T minus T0 multiply, and this will be a rho, this will be 1 upon rho. What is this specific volume? Specific volume is a 1 upon rho. So it will be P minus P0, and this will be rho into H0. So rho into H will be equals to this rho Cp T minus T0 plus P minus P0 plus rho into H0. Okay, this, so you can just revise. Okay, so I'm not very sure about this term actually. If this is, I think this will be 0. So this will be 0 integration P minus P0 at reference pressure, as it is constant. So temperature is also constant. No temperature. Okay, anyway, so will not go. So this will be there, rho into H. This is clear. Roll number 6, Aksh.
Yes, sir. Clear, sir.
So how to handle this rho into H? So this is actually rho into Cp T minus T0. With this input, so we'll try to solve this problem actually. Try to solve this problem. So now we are trying for a temperature profile. We are not interested in velocity profile. We are trying for temperature profile. Moreover, this velocity is constant. Velocity is constant and it is at V0. This velocity is constant. Almost superficial velocity or average velocity is constant. It is given velocities are constant, and we are interested in a temperature profile. So as this is insulated, here wall is insulated, reactor wall is insulated, there is no variation of temperature in R direction. Temperature of variation will be there only in Z direction. There will not. So this you can use a cylindrical coordinate system. There will not be temperature variation in theta direction also, because problem is symmetric around theta. There is no variation of temperature in R direction because wall is insulated, and there is a variation of temperature only in Z direction. So differential thickness will be only in Z direction. Okay, differential thickness will be only in Z direction. Roll number 8, Ali.
Yes, sir.
So what will be the flow area for heat transfer? Flow area available for heat transfer?
Sir, flow area will be, sir, so delta Z thickness.
Area.
Sir,
Flow
sorry.
area available for heat
Sir, area
transfer.
will be, sir, pi R square.
Pi R square, capital R
Yes.
square.
Yes, sir,
Okay.
capital R.
And what will be
Yes,
the
sir.
volume of a differential shell?
Sir, volume will be, sir, pi R square into delta Z.
Delta Z. And why we have taken a differential shell only in Z direction?
So because, sir, there is no variation in, sir, theta direction. And, sir,
Why
also
there
in,
is
sir,
no
Z
variation
direction.
of temperature in theta direction?
Sir, because of symmetry, sir.
Yeah. Why there is no variation of temperature in R direction?
Sir, because, sir, it's a plug flow, and, sir, it's a,
No. R direction. Temperature variation. Wall is insulated actually. Wall is insulated. Hence, there is no variation of temperature in R direction. Okay. So that can be also, it is given plug flow. Properties are constant as in radial direction. Okay.
Yes,
This is
sir.
also definition of plug flow. That is also correct actually.
Yes,
So rate of heat coming in, combined energy flux in the form of enthalpy. First we will write with combined energy flux only. Rate of energy coming in. How to get that, Ali? Rate of energy coming in.
sir. Coming in, sir. Sir, E
Coming
at
in the differential shell.
yes, sir. E at Z equal to Z.
Huh?
So into sir area
Area will be a pi r square.
pi capital R square into delta Z.
Pi r square only. Okay. Area, only area. What is the rate
Sir,
of energy going out from the differential shell?
yes, sir. E Z at sir Z equal to Z plus DZ into
Huh?
area pi R square.
And there is no any external process, heating or cooling is not there, but generation
Yes,
of
only-
heat is there. But how
Yes,
to
sir.
get
SC.
generation of heat?
So SC is given, sir.
SC, and that is per unit volume multiplied by
Yes, sir.
volume of a differential shell.
Yes, sir.
What
So
will be
SC
volume of
into
differential
pi
shell?
R square into DZ.
Okay, very good. So this rate of combined energy flux coming in, this is not there. External forces we don't have. External forces means heating or cooling. Energy production is there. So this is what energy coming in a differential shell. This is energy going out from a differential shell, plus this is energy generated or consumed. It all depends upon SC. For endothermic reaction, this energy is consumed. This SC will be negative. For exothermic reaction, this SC will be positive, and this will be volume that equals to 0. Now, what is next step? Nitin, roll number 9.
Hello, sir.
Next step. What is next step?
Hello,
Tell me.
sir. We'll divide by pi r square delta Z differential volume.
Very good. Divide by pi r square delta Z. Here you can see this r is different than what r we are taking in cylindrical coordinate system. Their variation of property was there in r direction only. This is a capital R. This is capital R. So radius of this is a radius of total radius of the cylinder. Divide by pi r square delta r multiplied by -1 and use the definition of differentiation. Use the definition of differentiation. What equation you will get, Nitin? So d by dz of Ez will be equals to minus SC. Roll number 9, Nitin.
Yes, sir.
Are you getting this equation?
Yes, sir.
Now this is for zone number 2. Okay, this is for zone number 2. What will be for zone number 1 and zone number 3, Aman? Because there is a variation, material is varying actually. Material is varying, so thermal conductivity will also vary. So overall material composition is changing, so effective thermal conductivity is varying. So hence this overall system is divided into 3 parts. There will be one model equation for zone number 1, one model equation for zone number 2, and one model equation for zone number 3. This is for zone number 2. What will be equation for zone number 1 and zone number 3? Aman, roll number.
Yes, sir.
Yeah, what will be the same similar equation for zone number 1?
Sir, for zone number 1,
Yeah, roll number 11, Chetan.
Yes, sir.
Yeah. What will be the equations, equivalent equation for zone number 1?
Mm,
Chetan.
yes, sir.
What will be the equivalent equation, similar equation for zone number 1? Roll number 12, Anand.
Sir, it will be
Yes, sir.
Anand, tell me. Anand?
Yes, sir.
Yes, sir. Yes, sir. You tell me what I am asking. Don't know. Anmol?
Yes, sir. Present, sir.
No, I'm not taking attendance. I'm asking what will be the equivalent equation for zone number 1 and zone number 3. Here, roll number 15.
Sir, just, sir, there should be no,
No, sir.
energy generation term, sir.
Huh? What?
Sir, we would not have the energy generation term.
So what will be the equation?
Sir,
D by
dz by dz equal to 0.
equals to 0 for zone number 1 also, zone number 3 also. That is what change will be there actually.
Yes, sir.
Accordingly, we will get the equation actually. So this is for zone number 2 only, zone number 2. So now can solve further, substituting this E. E will be equals to half rho V square rho into H into V plus this is a molecular flux because of viscous forces dot velocity plus Q. Moreover, this rho into H equals to, okay, this is okay, d by dz, substituting this in this equation. So this will be the equation for zone number 2. Okay, zone number 2, and moreover I can substitute this rho into H also. Rho into H will be equals to rho Cp T minus T0 plus P minus P0 plus rho into H0. Okay, substituting everything. Now certainly solving this equation will be very, very difficult. So most important message from the given problem, whatever problem we are solving now, is how to simplify the problem with a logical assumption. So solving this problem is important, but what we want to learn from this problem is how to simplify the problem as simple as possible so that it will fit to my actual experimental value. Whatever be the model equation I will be getting will be fit to my experimental value as close as possible. But as at the same time, it should not be mathematically very complicated to solve. Now you can see with this so many terms in the equation, if I want to solve, and for this is for zone number 1, zone number 2. For zone number 2, so SC will be equal to 0. For zone number 3, SC will be equal to 0. So I need to solve these 3 equations simultaneously. Certainly that will be very, very complicated, very, very complicated. So what kind of assumptions I can use? Roll number 15, Sai.
Hello, sir.
Sai. So what kind of assumptions you can use from the given problem so that you will get a simple mathematical equation instead of so complicated mathematical equation?
Sir, plug flow.
Plug flow.
Plug flow.
What is the properties of plug flow?
Sir, plug flow conditions means, sir, velocity is constant throughout the radius.
Throughout the radius. How that will be useful here?
Hello, sir.
How that will be useful here?
Sir, how that will be useful here?
Velocity is constant with respect to r. How that will be useful
Yes, sir.
here?
Sir, constant velocity along the radius we can't use, sir.
Yeah, along the radius you are telling or along the axis you are telling?
Sir, I'm telling along the.
With respect to z, we'll assume velocity equals to constant. There is negligible change in velocity.
Sir, dv by dz is equals to 0.
Yeah, dv by dz, a variation of velocity in z direction is assumed to be constant. As soon as
Yes, sir,
I
exactly.
assume this constant, this term will go. Okay, this term will go. This term will go because this is constant. This is constant. If this is constant, then this term will go. This term will go. Okay, as soon as I assume velocity is constant, this second term is also go. Rho Cp T0 into velocity, that will also go. This P0 into velocity, that is P0 into velocity, this term will also go. That is first assumption. Second assumption, a variation of pressure with respect to Z is negligible. So del P by del Z is small. Okay, because if there is no variation of pressure in Z direction, there will not be flow. There is a flow, but it is small to consider a temperature gradient. Okay, here we are considering temperature variation. So pressure has role to play in temperature in that viscous heating actually. So yesterday we have discussed. Okay, so because velocity is constant with respect to Z, pressure is negligibly small to contribute to any heat changes in Z direction. Heat changes in Z direction, hence P is considered to be constant with respect to Z. As soon as we assume this two small assumption, velocity is constant and that is equals to W pi R square by rho. This was also given, and pressure constant. This overall equation changes to this simple equation, very simple equation, rho Cp V0 T. So this is this term, rho Cp V0 T dt by dz. Okay, dt by dz. Only this term is there, and this is actually K effective for ZZ direction. Why it is written K effective? Because I have fluid also, I have this thing also, what I have solid particles also. So I am not considering a different thermal conductivity. I am considering a effective thermal conductivity for both phase together, effective in ZZ direction. Del 2 T by delta equals to SC. This is clear to everybody? So this is adding just two simple assumptions. Velocity is constant with respect to Z and negligible variation of pressure with respect to Z, so as to account in a heat transfer. Pressure is varying in Z direction, but it is smaller to account a variation of energy content in Z direction. That is why we can neglect this del P by del Z. Okay, anyway, this P0 is constant reference, and this is also constant. This is also constant. P, variation of pressure is there in Z direction, hence there is a flow. But this variation is not very high to consider a heat content, change in a heat content of the material. That pressure is not playing any important role in heat content or energy content of the material in Z direction. That is why this can be neglected. Okay, this is clear to everybody? Yeah, roll number 16.
Yes, sir.
Clear?
Yes, sir.
Okay. This is for zone 1. This is for zone 1 for this zone. Okay. So this is the equation for zone 1. Similarly, I can get the equation for zone. This is the equation for zone 2. Similarly, I can get the equation for zone 1 and zone 3. Now, I need to solve these three equations simultaneously. How many boundary conditions are needed to solve this problem? Roll number 16.
Sir, 4 boundary conditions.
4. How 4 boundary condition?
Sir, at Z equals 0.
Because, look, it is second order differential equation.
Acha,
How many boundary conditions are needed to solve this equation?
Sir, 2.
2.
6.
6. So what are 6 boundary conditions?
Correct.
Sir, we have 6 boundary conditions. So you can see, okay, at Z equals to minus infinity, here the reactant temperature is given. Okay, this is one boundary condition. Temperature is given for zone 1 here, that will be equals to T1. Z equals to minus infinity means reactant. At Z equals to 0, at this interface, there will be a continuity of flux and continuity of temperature. These are the two boundary conditions. So there is a continuity of temperature and there is a continuity of flux. This is the flux. Okay. Conductive flux. There is a continuity of temperature as well as continuity of flux. This is one boundary condition, two boundary condition, three boundary condition. Again, at Z equals to L, here at this interface, there is a continuity of temperature and continuity of flux. Okay, this 1, 2, 3, 4, 5, and sixth boundary condition is at Z equals to infinity plus infinity. A product temperature cannot be undefined. So certainly this this temperature here should be a finite. That is what the boundary condition is there. So now I have this three simultaneous differential equation and six boundary condition. I can solve this problem very easily. Okay. So any difficulty in till this? Roll number 17.
Sir. Yes.
Yeah. Got the problem? Now I have this three differential equation and six boundary conditions. So this problem can be solved. But still it is not so easy because this is second order differential equation. Second order differential equation and this second order linear differential, non-linear differential equation. So difficult to solve. So any input what you can give to reduce the difficulty in this problem. Logical assumptions to reduce the difficulty for solving this problem.
Sir, we can use boundary conditions, sir.
Yeah, logical boundary condition we are using anyway. This is logical boundary condition. I am asking about any assumption, more assumption you can add to this.
Uniform distribution.
Yeah, uniform distribution that already added. I want to simplify the given problem. Now this is three differential equations, second order differential equation, six boundary condition equation. This problem can be solved. You can get the temperature variation for phase 1, phase 2, phase 3. But still, if I want to simplify the problem, anybody else in the class?
Sir, we can find FT for different Z.
T for different Z.
Yes, sir, for Z less than 0.
I want to simplify the problem.
Hello, sir.
Sir.
Yeah, roll number?
48.
58. 48.
48.
Answer.
Yes.
Tell me answer.
Sir, we can assume like for Z less than 0, the both equations are equal, so we can assume that them to be equal to some constant C1 and then solve them independently to get C1.
Okay. That is when we will use when we have multi-parameter differential equation.
Okay, sir.
Okay, can you just recall everything? What is approximate this term is representing and what is approximately this term is representing? So this term is a representative of convective heat flux. Okay, you can see this V0 velocity is there, rho Cp into T is there, rho Cp into T into V0, and how this convective flux changing in Z direction. So this is the representation of convective heat flux, while this is d by dz of K into dt by dz. So this is the representation of conductive heat flux. Anybody can catch this hint? Okay, this is, we have discussed this previously also. Whenever there is a convection and conduction, it will be dominated by convection and this can be taken as a negligible. Okay, this can be taken as a negligible and we can neglect this. Because this is a convective transport of energy. This is the conductive transport of energy in Z direction only. This is also in Z direction. This is also in Z direction. But this is energy transported because of convection. This is energy transported because of convection. This is energy transported because of convection. This is energy transported because of conduction. So this will be negligible, or this will be smaller as compared to this whenever I will have convection and conduction. Okay, this we have discussed. So that input I can add here. So that input, this is the equation. These are the three equations. If I neglect the conductive heat flux, okay, this is the conductive heat flux. What is the equation I will be getting? Rho into Cp V0 dt by dz equals to 0. Okay, instead this is for zone 1, this is for zone 2, this is for zone 3. Now this is first order differential equation. I need only 3 boundary condition instead of 6 boundary condition. So as soon as I assume that conduction is negligible as compared to convection, conduction is negligible as compared to convection, this equation changes to very simple differential equation. Very simple differential equation. And what are these 3 boundary conditions? So instead of this 6 boundary conditions, so this was the problem, second order differential equation with 6 boundary condition. Now this needs only 3 boundary condition. So z equals to minus infinity, temperature is T1, and there is a continuity of temperature at z equals to 0, and there is a continuity of temperature at z equals to 0. So certainly solving this problem will be difficult, and solving this problem will be easier. Okay. And what is the difference between this problem and this problem? A small assumption. What is that assumption? Assumption I am considering the conduction is negligible as compared to convection. As given problem has both convection in z direction and this is conduction in z direction. So conduction is smaller as compared to convection. That is the simple assumption I have added. So as soon as this I am considering negligible as compared to this. So this is I am taking 0 as compared to this. So this problem reduced out to first order differential equation. Now this can be solved very easily. Okay, this you can solve very easily. So now you can substitute this f of t. What is f of t? F of t is given, f of t equals to theta. Okay, f of t is given theta. So t minus t0, t1 minus t0. This is given, and you can add this dimensionless z. Dimensionless z equals to z divided by L. L is the length of the reactor, and N will be a SC1 L rho Cp V0 T minus T0. Now rearranging this equation, what you will get here for this equation, you will get d theta 1 by dz. This is for phase 1. D theta 2 for phase 2, z equals to n into theta 2, and d theta 3 dz equals to 0. This z is the dimensionless length actually, and this is dimensionless temperature. F of t is given. Okay, and this boundary condition will change to, so at z equals to minus infinity, capital Z will be equals to minus infinity. So theta 1 will be equals to 1. So at z equals to minus infinity, theta 1 equals to 1. At z equals to 0, theta 1 equals to theta 2. At z equals to 1, theta 1 equals to theta 2. Theta 2 equals to theta 3. Now solving this equation is very easy. Now integrate this equation first. Use this boundary condition. Then whatever you got, use this boundary condition to get this value here, and use this boundary condition to get this value. Anybody has any confusion over here? Now this can be integrated. Okay, the first equation d theta 1 by dz equals to 0, theta 1 equals to c1. So at z equals to minus infinity, theta 1 equals to 1, hence c1 equals to 1. So first, so solution of this equation will be theta 1 will be equals to 1. This is the solution of this equation with this boundary condition. Now at z equals to 0, theta 1 equals to 1. That will give me, okay, this is second differential equation. Integrating this second differential equation, theta 2 will be equals to c e raised to nz. Okay, c e raised to nz. So that will give me a second differential equation, and this I can use z equals to 0, theta 1 equals to theta 2. At z equals to 0, here you can see theta 1 equals to 1, hence theta 2 equals to 1. So at z equals to 0, theta 1 equals to theta 2. At z equals to 0, theta 1 equals to 1, hence z equals to 0, theta 2 equals to c, hence c1 equals to 1. Okay, this capital C equals to 1, hence theta 2 equals to e raised to nz. E raised to nz. This will be the solution of this second differential equation with this boundary condition. Theta 2 equals to e raised to nz. Now substituting this is at z equals to 1. At z equals to 1, theta 2 equals to e raised to n. Now this will be used for third boundary condition, third differential equation. So integrating this equation, C3 will be equals to e raised to n. Solving this, you will get theta 3 equals to e raised to n. So this is what I got. For zone 1, theta 1 equals to 1. For zone 2, theta 1, theta 2 equals to e raised to nz. And for zone 3, I got e raised to n. Okay, this will be a temperature profile T. Okay, T minus T0 divided by T1 minus T0. Theta 1 is nothing but the temperature profile. If I plot this, so you can see from z equals to minus infinity to z equals to 0, theta 1 will be equals to 1. And for z equals to 1 to z equals to infinity, this will be equals to e raised to n. For n equals to 1, for n equals to 2, for n equals to minus 1, minus 2. If you have endothermic reaction, this n will be negative. So this will be the temperature profile. And this will indicates n equals to minus 2 means more intense endothermic reaction. This is less intense endothermic reaction. This is at n equals to 0, it will be constant. Temperature will be constant. There will not be any heat generation. So temperature will be constant at n equals to 0. That will be neither endothermic, no reaction at all. This will be lesser exothermic reaction. This will be more exothermic reaction. This will be the temperature profile for zone 2 and this will be temperature profile for zone 3. So this is what when f of t is given for any arbitrary function, let's say f of theta, any arbitrary function. So this will be a temperature profile for any arbitrary function. For this zone 1, theta 1 will be equals to 1. For zone 2, it will be integration of this arbitrary function d theta n, that will be equals to nz. And for theta 3, it will be equals to theta 2 estimated at theta 1. This will be for any arbitrary. Now you put any theta, any f of theta here. So accordingly, you will get this temperature profile for any arbitrary function. Okay. So this is what all the three information we got. So first of all, we got the temperature profile and how it is varying with n, and this is how we got for any arbitrary function. This thing f of theta. Anybody has any difficulty in this problem? Go home and do all these mathematics, very easy mathematics. Okay, this very easy mathematics, how to solve this. And this is how it is varying for, this is highly endothermic reaction, some lesser endothermic reaction. This is exothermic reaction, lower exothermic reaction. This is a highly exothermic reaction. Theta 1 will be at 1, zone 1, and this will be also constant. There will be increase in temperature for exothermic reaction, while there will be decrease in temperature for endothermic reaction. And for any arbitrary function f of t, so here this is only the catch. I will be integrating for this f of theta, 1 upon f of theta d theta equals to nz. And I can substitute it here, and accordingly I will be getting the temperature profile for phase 1, phase 2, and phase 3. Anybody has any doubt?